All right, welcome to The Explainer. Today, we're going to pull back the curtain on the hidden brains behind, well, pretty much every modern industry. The Programmable Logic Controller, or PLC. It is the silent workhorse that keeps our world running, and we're about to break down exactly how it works. When you look at a control panel like this one, packed with all that hardware, it just looks incredibly complex, right? You have to wonder how it all works with such perfect timing. But the truth is, all of this, it all starts with one single fundamental command. So let's dive in and see what that is. So let's start at square one. The absolute foundation of a PLC's memory is this one little instruction, set/reset. Seriously, everything else we're going to look at today, it all builds from this single concept. Just think of a regular light switch, but this one's got a superpower. You just give it a quick tap, a momentary signal, and it remembers to stay on. You don't have to keep your finger on the button. It has a memory, and that's the key. So, in the PLC world, we often see this drawn out in what's called ladder logic. Now, it's designed to look just like an old-school electrical diagram, which is super helpful for electricians to understand. And you can see right here, one signal comes in to set the device, turn it on, and a totally different signal is used to reset it, or, turn it off. Okay, but here's where it gets really clever. The PLC is constantly reading its code in a loop, right? Top to bottom, over and over again, super fast. So what happens if it gets two conflicting commands at once? Well, the last one it reads is the one that wins. That little rule is absolutely crucial. It stops the whole system from getting confused and locking up. Let's see how we can use this in the real world. So this simple little memory switch we've been talking about, it's actually powerful enough to solve some really common everyday problems, like, say, automatically keeping a water tank at just the right level. Okay, so here's the setup. We've got a tank, a pump, and an inlet. The system needs to know two things, when the water's too low and when it's full. For that, we use two sensors, a low-level switch and a high-level switch. You can think of these as the eyes and ears of our PLC. And here's the logic kicking in. The water level drops, it hits that low-level switch, and boom, that sends our set command, the pump motor fires up, and the tank starts filling. And this is where that memory part really shines. Because the logic is latched, the pump doesn't just shut off once the water's above the low sensor. Nope, it keeps running, all the way until the water hits that high-level switch. That's what sends the reset signal. This is so important because it keeps the pump from constantly clicking on and off, which would just burn it out. Okay, that's perfect for one tank. But what if your factory has, 10 tanks? Or 100. You can't just copy and paste that code 100 times. That would be an absolute nightmare to maintain. You need a smarter, much more efficient way to handle that. And that brings us to two really powerful tools in any programmer's toolbox, functions, or FCs, and function blocks, or FBs. Now, if you just glance at the code, they can look pretty much the same. But trust me, there's a huge difference hiding under the hood. So what's the big difference? It all comes down to memory. A function, the FC, is what we call stateless. It's like a simple calculator. It does a quick calculation for you, gives you the answer, and then immediately forgets everything. But a function block, the FB, that's different. It has its own dedicated memory, which we call a data block. What does that mean? It means you can write one master FB for a water tank and then reuse it for 10 different tanks, and each one will remember its own status, its own pump, its own water level. It's a total game changer. Okay, so we've made our software smart and scalable. That's great. But what happens if the actual hardware, the physical PLC box itself, just dies? In some industries, think power plants, chemical factories, failure is just not an option. You can't let that happen. Well, the engineering solution for this is a concept called redundancy. And it's actually a pretty elegant idea. You basically give your PLC a co-pilot. If the main one runs into trouble, the backup is right there, ready to take the controls in an instant. On a whiteboard, it looks pretty straightforward, right? You've got PLC A, your primary, and an identical PLC B, the backup. They're running in parallel, constantly checking in with each other, just waiting for the signal to take over if anything goes wrong. And this is what that looks like in a real control cabinet. You can literally see two identical CPUs physically connected. If that primary unit on the left has any kind of problem, a power surge, a hardware fault, anything, the system automatically and seamlessly switches everything over to the backup on the right. But here's a key thing to understand. Not all redundancy is the same. And this choice isn't just about technology, it's a business decision that boils down to risk. A warm redundant system, for example, might have a tiny fraction of a second of downtime during that switchover. For a lot of processes, that's totally fine and way more cost-effective. But if you're running a power grid or a multi-million-dollar pharmaceutical batch, you need hot redundancy. The extra money you spend on high-speed fiber optics is a no-brainer, because even a millisecond of downtime could be catastrophic. So, even with all this incredible engineering, with redundant systems and smart code, stuff still happens. I mean, wires can break, components can wear out. So, how does a technician on the factory floor figure out what went wrong? It really all comes down to a logical process of elimination. You don't just jump in and start messing with the code. No way. You start with the absolute basics. Is everything plugged in? Is it getting power? You check for simple stuff like loose wires. After you've checked all the physical stuff, then you look at the little status lights on the device itself. And only then, as a last resort, do you plug in your laptop and dive into the deep diagnostics. You always go from the simplest possible explanation to the most complex. And those little LEDs on the front of the PLC, they're telling you a story. A nice, steady green run light, that's what you want to see. Everything's happy. But if you see a red light like SF for system fault or BF for bus fault, that's a huge clue. A bus fault, for instance, tells you right away that the problem probably isn't the PLC's brain. It's somewhere in the communication network that connects it to all the other gadgets. So just step back and think about the journey we just took. We started with a single, simple command that just remembers to keep a pump running. And from that one idea, we scaled up the software to be incredibly efficient, and then we built a fortress around the hardware to make it practically unstoppable. We've built a truly resilient, fault-tolerant system, all from that one simple block. You know, we've seen the incredible power here of building these complex, super reliable systems from the most basic building blocks. But it does leave us with one last really important question. The system can be designed to execute logic perfectly. But what happens when the logic we humans program into it is flawed?